We have Giri Gopalan. He is a staff scientist in the statistics group at Los Alamos National Lab. He focuses on statistics in the physical sciences, things like spatiotemporal statistics and uncertainty quantification. And here he's going to talk to us about applying those uncertainty quantification approaches to foundation models.
Thanks for the introduction, and it's great to be here. It's the first time I've been to DataWorks, so it's been a lot of fun being at a new conference. I'm with Los Alamos National Laboratory, and I'm involved with the project on foundation models for non-proliferation. And before I begin, I just want to emphasize the contributions of other people that I've been working with, especially Rachel, who is a PhD student at UC Irvine in statistics, and she has helped with a lot of the visualizations and things that you'll see in this talk. And Emily is also involved and has been leading this effort. Okay. So we've heard a little bit about foundation models and things like ChatGPT. And essentially what a foundation model is, and I'm going to say essentially because there's not really an accepted definition, but think of a really large deep neural network, these days typically transformer architectures that are adapted to solve a variety of tasks. So adaptation could be a number of things, but something like fine tuning, which we heard about previously. And what is typically done to assess foundation models is to benchmark them on a corpus of different tasks. That's sort of what has been done, at least traditionally. Maybe there will be some improvements. And sort of what this talk is about is how we can involve uncertainty in a variety of ways, and why it's important to involve uncertainty when doing this benchmarking. There are a number of different issues when you benchmark that are delineated here. I'm not going to go through all of them, but we're going to focus on things like how do we aggregate metrics and how do we put them on the same scale? And importantly, how do we involve uncertainty when we do this aggregation as well? Okay, so to illustrate some of the things we've come up with, and essentially what you'll see, the theme of this talk is I said a statistical framework, just use statistics. It could be a simpler title, but essentially you have two case studies that we have explored, which will demonstrate some of these statistical methods to involve uncertainty in benchmarking foundation models. So the two are VTAB and MMLU. I'm getting used to using a lot of acronyms, but what that stands for is Visual Task Adaptation Benchmark and Massive Multitask Language Understanding Benchmark. The first one's an image-based benchmark, and the second one is a text-based benchmark. And what you'll see is amongst the various benchmarks that exist, usually you don't have uncertainties, and you also sort of do simple things like just take unweighted average of scores across different tasks. And we're going to try and improve upon that a bit. So VTAB, for instance, just to give you an example of what that looks like, you have images that are in three different categories, and you have tasks like classification. For instance, in the specialized category, do you see some metastatic tumor? In structured, the questions are like, what's the depth of a certain object in the image? Natural is, the typical classify cats and dogs kind of thing that you'll see in machine learning. And so the numbers of tasks in these benchmark data sets are delineated here, but it's important to note that they're actually subsampled. And so you end up having 7,000 in natural, 4,000 in specialized, and 8,000 in structured. MMLU is the text question and answering benchmark that I mentioned before. And there you have questions that are in 4 different categories as opposed to 3, like the previous one: humanities, social sciences, STEM, and other. Covering a variety of topics like mathematics, history, computer science, law, etc. Okay, so these are the benchmarks we looked at. And typically when you see a leaderboard in machine learning, you sort of, okay, yeah, I get this score in this category, a different score in the next category, average everything together, get one number and just call it a day. Super rotation 100% is the best, right? Similarly for MMLU. And sort of what we're going to argue is that if you do some statistical thinking, you can sort of involve uncertainties without too much hassle that will maybe tell a more accurate picture of these foundation models. Okay, so the first way to do this is something that probably many people here are familiar with, is just bootstrapping. And essentially what we're doing is we're resampling the task items with replacement. And for each resampled set, we can aggregate metrics however we want. Right, so that's what this is illustrating here. Just to dig deeper a little bit, so we only have aggregate scores for a lot of these tasks. So what we do is we assume, okay, if we know that the accuracy is 95 out of 100, we essentially sample with a displacement a vector of 95 ones and remaining zeros to get variation for the accuracy score over repeated sampling. And we can do this for different tasks and different models. Okay, so this is probably the most straightforward way to involve uncertainty in these benchmarks. And what you end up seeing, though, is that the picture is interesting because you do see overlap, for instance, in these first few overall accuracies. So it's not a very complicated story, but the story is if you involve confidence intervals in some kind of meaningful way, you can elicit where models are actually more similar than you might originally think. Just this is a similar thing for the MMLU leaderboard. You can see here that similarly, there's overlap in these intervals, right? These first few overlap as well. Okay. Now here's another issue that I sort of pointed out in the first slide, and I'll go into a little bit more deeper, but I think this is a really important one because a lot of benchmarks, like I showed before, will just take unweighted averages across metrics, across different tasks for each of the foundation models and use that as a comparison point. But of course, there are many reasons why we may not want to equally weight different types of tasks. Some of them may be more difficult than others. Some of them may vary in the quality of questions being asked, the number of questions being asked. And so we came up with a way to sort of visualize foundation model performance when you have different weighting mechanisms, and that's what I'll explain next. Okay, so these series of plots are sort of illustrating what I mentioned here. So if you take this first plot here, what we're showing is essentially a simplex where each point on the simplex corresponds to a different weighting mechanism across the three different categories of tasks. Right, so for instance, if you're around here, this would be 50% weighted to natural, 30% weighted to structured, and 20% weighted to specialized tasks. And this is a really good illustration of why involving uncertainty matters to some extent. So if you look at this first left plot, everything is colored and it's not gray. There's no gray coloring, and gray stands for indeterminate. So in this first plot, we're not involving uncertainty at all. What we're saying is we're going to color a particular point if the corresponding model is the best in an absolute weighted average sense, right? So if the weighted average for that particular model is better than the other ones for that particular set of weights on this plot, we say that one's the best. So if you were to just first look at this and not think about uncertainty, you would probably conclude that, okay, yeah, you know, this super rotation 100% model is indeed the best one. Now the story kind of changes if you start to include uncertainty. And the way we're doing that in this particular example is we're calculating a standard error, right? So think of confidence intervals essentially with some confidence intervals. And we're saying, okay, we're only going to declare a particular point the best if it's more than one standard error away from the second place. Otherwise, we say it's a tie, right? So you can see here now all of a sudden, it's not a very clear-cut winner. And in fact, if you go all the way to 2 standard errors, essentially there's really not much of a difference at all, except there is this little pink blurb here, and that's kind of important because essentially what it's saying is if you care primarily, if you weight structured images very highly, then the rotation model does the best. And that makes some sense intuitively because if you recall, the structured category had things with the depth and shapes and things like that, right? So kind of the moral here, or the takeaway is that, yeah, uncertainty matters a lot. And it can also help you understand, when certain models do better than others. Okay, so this is repeating a similar thing for MMLU, the language benchmark, except the difference is, or one of the differences is that there are 4 categories, a little bit trickier to make the same triangular plots as we had shown previously. But essentially here, what this is showing is that a particular line is saying, okay, for this particular set of weights on these 4 different categories, this model performed best with a tolerance of 1 standard error. So we only declare something best if it's more than a standard error away from the second place, right? So there are still many indeterminate weightings, but you can see some interesting things. Like for instance, for this model, POM 540B, what you see is that if you have, there's sort of an interaction between humanities and social sciences. So if you kind of, if the sum of these is near 1, essentially, so if you're upweighting both humanities and social sciences, but downweighting the others, then actually POM 540B tends to be pretty good. So this is kind of a way of visualizing, task weightings. Okay, so the primary way I discussed how to do uncertainty quantification with these benchmarks is to do bootstrapping, right? As a statistician, especially someone who's liked using Bayesian methods before, I kind of wanted to see, okay, can we do something maybe a little bit more complicated? And so we toyed around a little bit with Bayesian hierarchical modeling. Some people in the audience might be familiar with that. And this is actually mentioned in a paper in the literature by Rachel's advisors, one of the co-authors, but we hadn't seen an implementation. So we said, okay, let's just build a not very complicated Bayesian hierarchical model to model evaluation data on VTAB and MMLU. And sort of the textbook reasoning for why this is a good idea is that you can sort of borrow strength across different instances. In this case, essentially, there's a common distribution for the accuracy of a foundation model across different tasks, right? Okay, and then eventually what we're going to do is we're going to sample from what's called a posterior predictive distribution of task performances to get uncertainty over our assessment of foundation model performance. Okay, so this is the model. If anyone's taken a Bayesian model class, it's actually not a terribly complicated one. What we're saying is that Yij is the number of correct responses for foundation model I on task J. Theta Ij is the probability of an accurate response for foundation model I on task J. And so what we're saying is, okay, conditional on these theta parameters, the number of Yij follows a binomial distribution. And then we put a beta prior on the thetas, but then the hierarchy is that we have another level where we actually put a distribution on the alphas and betas, which is common for each of the foundation models. Okay, so this is the way we're borrowing strength. If anyone's here has worked with Bayesian hierarchical models, well, this part is easy to deal with in the sense that it's a beta binomial situation. You have a conjugate prior, so you can get the posterior easily, but this is not conjugate. So I coded up a Markov chain Monte Carlo algorithm, MCMC, to do the sampling of these parameters. This is just one of these things that statisticians like to show that, oh, my things are working okay. Like if this is not a fuzzy, what's called a fuzzy caterpillar, I don't know why that description is used, but then things are out of whack. But okay, things are okay, so that I'm convincing myself that the algorithm ran okay. This is just what's called a posterior predictive check. So what I'm doing is I'm sampling from the posterior predictive distribution and comparing the observed data, and this is for a specific variable. And essentially, if this is out in the tail somewhere, that says that, oh, the data isn't really, there's a poor model fit, essentially. But this is convincing myself, okay, yeah, the posterior predictive distribution looks okay. And then what I did was I compared the Bayesian hierarchical model and the bootstrap intervals. And what you tend to find for both MMLU and VTAB is essentially that the intervals for the Bayesian hierarchical model did end up being slightly wider, but in a practical sense, there's really not much of a difference in terms of overlap and conclusions that one would draw. So essentially, this is summarized here. And I did another test, which is just empirically, asymptotically, if I get more data. So if I assume that these benchmarks have more data and sort of just multiply the number of accurate responses, do I end up in proportion, that is? I end up finding that there's less of a difference between the Bayesian hierarchical model and the bootstrap. So operationally, I think in this setting at least, there isn't that much of a difference using either of these methods. Of course, if I used a more informative prior or something like that, maybe I would get different things, but I kind of use very diffuse priors here. Okay, just a few more things I'd like to talk about. that's sort of the framework that we are developing. One might ask, well, what if you had things that are not accuracies, right? So everything that I've been working on or showing you so far has involved accuracies for these foundation models, but you could also think of if there's a continuous prediction task or something, you could have root mean square error, something that grows without bound. And so the solution we're thinking of right now isn't very complicated. It's essentially standardized by taking the raw score, subtract off the low score, and then divide by the range. And then the advantage of this is, of course, if we transform everything to 0, 1, we can essentially use the same kinds of thinking we've been using for accuracies, given those are 0 to 1. Now, there are some complications. It's not as simple as I mentioned. For instance, how do you actually find these high and low scores? You could either think of a couple ways. One would be have some big benchmarks. For instance, the high or low, like your worst performing model will tell you your low score, something like that. You could also try estimating from the data. For instance, you could use the high and low in each bootstrap sample as the estimate, and we've done some work on that. But this is at least one way to do it. And then finally, I just wanted to talk about rank aggregation procedures. The reason I'm mentioning this is that in the literature that has been suggested in some cases. In fact, there's a paper in JRSS, the Journal of Royal Statistical Society, Statistics in Society. And basically, we shall repeatedly emphasize the need for interval estimation in which the uncertainty associated with estimates or ranks is explicitly displayed. So this is something that statisticians have cared about well before foundation models. This is, I think, a 96 paper. Essentially, thinking about ranks and uncertainties there is also important. And one of the advantages is that if you work with ranks, you kind of throw away this issue of having to standardize scores, right? Because you don't have to, once things are ranked, they're essentially on the same scale, right? So that is a nice thing, but it's not all easy. So the simplest thing you can do is this thing called borda count, is essentially rank by average rank, right? So for each task, you rank all of the foundation models, you average ranks across the different tasks, and then you rank models by the average rank. Okay, so that's one thing you could do. And you could also get confidence intervals in a similar way where you bootstrap, or you could use the Bayesian hierarchical model, whatever you want. But there's kind of a more sophisticated way of doing this, which is called, hopefully I'm saying his name right, Kemeny consensus, a famous Hungarian mathematician. And so essentially the idea of that is, so you can think of this previous procedure as an approximation to this consensus ranking. And what is the Kemeny consensus? Essentially, given a list of ranks, you want to find a consensus rank that minimizes the average Kendall distance between the consensus and the list of ranks. Okay, so there's some things to unpack there. So first of all, what is the Kendall distance? Okay, so it's the number of times there's an inversion between the two ranks. What's an inversion, right? So for instance, here, what we're going to do is every time that object A is ranked higher than object B in the first rank, but the other way around in the second rank, that's an inversion, right? So here, so if this is A, B, C, and D that we're ranking, A is bigger than D, right? Whereas here, A is smaller than D, whereas here, A is bigger than D. 1 is smaller than 4, and here 4 is smaller than 3. So that's an example of one inversion. You could go through this for all pairwise combinations and then count how many times there's a difference. And so for example, here, this is an easy one because, okay, well, 3 is greater than 1, 2 is greater than 1, 3 is greater than 2, but 2 is greater than 3, right? So that's an inversion. So you can go through examples. And so there's actually a paper in NeurIPS, which is a very, a big top machine learning conference that essentially is suggesting, use this Kemeny consensus when you're comparing foundation models and you have many different task scores. Now, one thing I found that was interesting, though, is that it's not really pointed out in the paper, is that, yeah, it satisfies a bunch of nice properties. It was proved in the Applied Math Journal thing in the 70s and comes from like voting, political science kind of literature. But it turns out there's no need to have a unique consensus. So when I put this into a particular R package called cons rank, you end up not having a specific unique solution. So while certainly one can exist because you're minimizing this distance, so you can, yeah, sure, you'll find one. It's not a unique solution. And so there's some uncertainty here. And in fact, this is uncertainty that isn't due to sampling variability, which is kind of what I was harping on before. This is just due to the fact that there's no unique consensus. So to visualize this, what you could do is make a bar plot where you say, okay, what is the proportion of consensus ranks for which a particular model is ranked I, where I is on the x-axis. So for here, for instance, this would be, this codex replug is mostly 1, but sometimes 2. This is mostly 2, sometimes 3, et cetera, et cetera. So that's another way of sort of displaying the uncertainty inherent in these ranks, right? And I guess the last thing, yeah, I will sort of touch upon is that you can also think of different Bayesian ways to do this. So far, the 2 other ranking methods I mentioned, I haven't really specified or harped on Bayesian methodology. There are Bayesian ways to do this. So for instance, there is something called the Thurston-Mostiller-Daniels latent variable model, which you can kind of run on this Bayes rank analysis R package. And then you get posterior probabilities for ranks. And then you can also do the same thing with the Bayesian hierarchical model I mentioned before with beta binomial, where instead of ranking by this latent parameter, you are ranking by some combination of the accuracies of each of the foundation models in aggregation. So this is maybe a little bit more expressive because you can, again, explore different types of weights. So for instance, if they're all equal weights, you find that, okay, probably the highest probability for codex is that it's rank 1, but there's some probability being rank 2. If you remember that example with humanities and social science being weighted high, you get a similar thing here, right? The POM 540B model ends up being ranked first with a fairly high probability, and the things flip for the other models. So this is just to say, again, you can use a Bayesian model to ascribe probabilities to different ranks. Okay, I guess I'll just mention my last thing to mention here is that so far, everything that we've worked on is sort of ascribing probabilities to metrics on these foundation models, but we haven't really thought about like putting predictive uncertainties on the outputs of foundation models, and that's sort of what we're thinking about next. So in other words, we heard about fine tuning. So is there some way you can determine the uncertainty that is derived by fine tuning, some small part of the network? And so there's some different things in the literature like split conformal inference, resampling, like I had mentioned before, bootstrapping, maybe ensemble methods. So these are things that are sort of to come in the future. Okay, and that's it. Thank you for your attention. If you have any questions or you want to chat later, I'd be happy to. Thanks.
For questions, if anyone has any.
Question. Have you seen much literature, not just comparing different models, but looking at one model and describing the uncertainty due to maybe a lack of training data or test data within one domain versus another domain? So a model performs very well because it's playing test data in one domain, whether that's, I don't know, the social sciences or whatever we're describing up there. But you don't have a lot of test data in a different domain. Mm-hmm. Do you see ways to quantify that risk that you're assuming if you're going to use the model in both?
Yeah, so I think the literature, if I'm not mistaken, it's referred to as out of distribution testing and that kind of thing. One way I've thought about doing something like that would be sort of reweighting test examples that you have that are more in such a way that you're describing like this different domain more realistically. So that's a thought, but I haven't done too much on that. Thanks.
I'd like to comment on that. I've only seen one method that tries to address that sort of partially. And that's to do a systematic inclusion-exclusion study where you basically include or withhold training data along some sort of like data feature axis that describes, the out of distribution that you want. So you have your data. If you can figure out where your out of distribution data lives, you could try to do an inclusion exclusion study to figure out how your performance changes as you either have access to data along that direction or don't. And then that gives you a concept of how your performance will change once you go over there to your distribution.
That's assuming you're retraining it.
Yes.
Step along the way, not.
That is absolutely what it is. It is expensive, it is computational, it is very slow. That is the only thing I've seen that tries to address that question with some success.
Okay.